I hope the homework is going well. If you are having any problems, please let me know, either via email or personal contact. But what we're going to move on to now is friction. And in friction, I have more good news for you. The good news is I didn't tell you any half-truths last year. So anytime that we are having solid on solid contact, you are always going to be able to work with the same exact stuff we did last year. Okay, as a basic reminder, anytime that we're dealing with the force due to friction, the force due to friction is always going to be having to do with some coefficient of friction times the normal force. Alright, the normal force obviously is how much force is being acted on between those two surfaces, and mu is the coefficient of friction. Basically, this is just a multiplier that is based upon the different materials that are involved. Rubber is obviously going to have a higher mu value, a coefficient of friction value, than Teflon or greased steel or something along those lines. Now, the key things to remember here. Friction always opposes motion. Alright, what that means is any time that you have two objects that are going to slide past each other, friction is going to act in the opposite direction of the motion. If you really think about it, when you're pushing back on the ground with your shoes, what's actually happening is friction is propelling you forward. So I'm not saying that friction is always a bad thing, but it is always going to go in the opposite direction of your general motion. Right? There are two different types of friction. The two different types are static, and that is denoted by mu sub s, and kinetic. Kinetic is mu sub k. Alright? Static, in general, tends to give you higher force values. Okay, I know it looks like valves, but I meant values, right? The static friction basically means that it's going to take more force to get something started than it is going to use to keep it going, right? These are going to tend to be lower values. This is why your car having anti-lock brakes is designed to use this fact. If you were to lock up your brakes, you were to have less control over your vehicle in a sudden stop situation. So by locking your brakes, you would create a kinetic situation where the road surface is actually sliding past the tire. By not allowing your brakes to lock up, you're keeping it in a static situation. Now granted, it is many instances of static friction, one right after the other, but still, you're going to end up with the same general trends here. It's a higher value for static than it is for kinetic. Okay? Now, I'm not going to waste time going over a simple situation with this. I am, however, going to waste time going over a more complex situation with this. So let's say that we have a... you know what? I'm going to make it even more complex than what I originally made. This isn't too bad, though. Let's say that we have a 5-kilogram book. And that 5-kilogram book is being pushed against the wall with a force of 12 newtons. Pause for one moment. You have my apologies. Didn't mean for that there. Had a student walk in. Okay, now, you're applying a 12 Newton force against the wall. The coefficient of static friction between the book and the wall is 0.6. The coefficient of kinetic friction is 0.4. Okay? Now, here's the question. Will the book fall? Okay. Now, so I'm applying a 12 Newton force against the book. Now, what you need to understand first is what's going on here. If I'm pushing with 12 newtons against the book, then the book is therefore pushing with 12 newtons against the wall. If the book is pushing with 12 newtons against the wall, that means that the wall is pushing with 12 newtons off of the book. I could have solved that in a different way. The sum of the forces in the x direction equals 0. I know that there are two forces that are involved, the push down on the book, and there's also the push back from the wall, which is 12 minus, in this case right here, this becomes a normal force. The reason it is a normal force, it is a contact force between two surfaces, and it is pushing back at a normal. So in other words, that means that my normal force here is 12 newtons. Okay? Pretty simple. So what I need to do here is I need to determine whether the force of gravity is going to be larger than the force of friction acting up on the book. So let me start with a free body diagram. Here's my book. My normal force, which I know to be 12 newtons. The applied force, which is 12 newtons. So in other words, it will not be accelerating left and right, which would be expected. So we'll go with that. Now, the natural motion of this book would be to fall down. The reason it would fall down is it has a weight. That weight equals its mass times gravity. Now, anytime that you draw friction, I wasn't a stickler for this last year, but I'm going to be this year. It's important to connect a line from the surface that is interacting with the friction, that is having the friction, and then connect it to the direction that it will be going. So in other words, the force due to friction is right there. Okay? Now, here's where things, you can simplify them if you would like. Now remember in the last problem when we had the incline, alright, we took and we rotated the reference frame to make it more similar to situations that we have done before. If you would prefer to do it like this, you are welcome to do so, because then your normal force will be acting up. You would be the equivalent of having a force acting in this direction here and friction pulling back. It's up to you how you want to solve this. The nice thing is, you can make this look like a problem that you may have already solved, and by doing so, you can make this problem inherently easier. Okay, so let's say I'm going to leave it like this because everything is still going to act out the same exact way. Now the first thing I need to do is determine whether the weight is going to be enough to break my mu static times my normal force. Alright, so weight is mass times gravity equals 5 times 9.8, which would be, here's my calculator, 5 times 9.8. 49 newtons. Okay. Now, mu static times the normal force. I know my normal force is 12. My mu static is 0.6. Well, this is going to be fairly obvious what's going to happen here. The force due to friction, the biggest force that I can get due to friction is going to be from my static case, which is going to be 0.6 times 12. 0.6 times 12 is 7.2 newtons. Now, what I need to determine is, will the block fall? In other words, which one of these forces is larger? If the bottom force is larger, that tells me that it is going to fall. Now, here's the big thing about friction, and the big thing to remember is, if this force of friction happened to be larger, that does not mean that the object is going to just start accelerating up. Frictions will cause accelerations, but they will not cause accelerations in directions opposite to motion naturally. or I'm sorry, they will not cause an acceleration, a motion naturally. I apologize. That's what I meant to say. They will not cause an acceleration or motion by themselves. The only way that you can have this friction that will actually change the situation would be as if it was 49 newtons or larger. Now, let's say that if this case had it that the force due to friction up here was 65 newtons. It's important to be able to read that the force due to friction is larger than the force that is acting on it. Therefore, it's not going to accelerate up. It's going to be in equilibrium. So in this case here, the force due to friction acting up would only be 49 newtons. Okay, so these problems are not any more difficult than anything we've done before. You may see these types of problems on inclines, you might see them in a different situation, but they're still going to be the same basic thing. All right, I'm going to pause off this video here and use the next one to talk about friction in the case of fluid friction instead of solid friction. So at the end of the next video lesson will be your next homework assignment. So be ready.